Hi everyone, I'm Yang Niu from Scientific Software Lab, China University of Petroleum, Beijing. And today I'll give a presentation on our work, TileSpGEMM, a tiled algorithm for parallel sparse general matrix multiplication on GPUs, cooperated with Zhengyang Lu, Haonan Ji, Shuhui Song, Zhou Jin, and Professor Rifeng Liu. SPGEMM multiplies two sparse matrices A and B and gives a resulting sparse matrix C. And the classic SPGEMM is a row-row style method. Take the figure below as an example. When calculating the first row of C, all the non-zeros in the first row of A are used to scale the corresponding rows of B. And the intermediate products are inserted or added to the temporary space. So calculating each row of C is independent of each other and easy to be parallelized. SPGEMM is a key kernel in third level Sparse Plus and has a wide range of applications such as algebraic multigrid methods in sparse linear solvers and breadth first search in graph processing unit and deep neural network in machine learning. So, however, despite lots of effort in the optimization of SPGEMM, there are three performance issues that the row-row style method inherently have. The first one is a load imbalance. So when we record the number of the intermediate product of each row of C, we can find that the number of the intermediate product of each row is very imbalanced. When we deal with very large scale matrices like web-based, the load imbalance is become more obvious. So it is so hard to saturate massive parallel GPUs when a small number of long rows dominate runtime in the row style. And the second issue is about the size of C. So as we mentioned before, the resulting sparse matrix, the resulting matrix C is sparse and the size is unknown. So that means that when we want to calculate C, we first have to do a symbolic SPGEMM to obtain the number of the non-zeros. And after allocating the space for C, we then can perform the numeric SPGEMM to get the final result. And during the process, we have to perform twice SPGEMM actually, and we require space for a large amount of immediate products. So it is so hard to allocate a proper size at runtime. And the third one is the sparse accumulator selection. In recent years, researchers have been working on designing efficient sparse accumulators. However, the row-row method inserts non-zeros to random position in a rows of C at unpredictable sparsity. So it is so hard to design a sparse accumulator to efficiently accumulate new entries. So the three performance issues motivate us to design a totally different data structure, and we call it tiled data structure. And giving a 16 by 16 sparse matrix, we no longer store it by the row-row style. Instead, we store it as a number of sparse tiles and use them as a basic computing unit. Thus, the load imbalance issue can be naturally avoided. And we use two levels of information to store the sparse matrix. The higher level stores the tiles information, and it includes three arrays: tile color index array, and the array, and tile pointer array. And finally, we will make the prefix sum operation for the array for the future computation. And the specific information of non-zero in tiles are stored in the lower level with a combination of CSR and COO format. Plus, we add a mask array to record the bit mask of a sparse tile, and specifically mark 1 in the column index position, corresponding column index position, and mark 0 otherwise. So that's the whole the tile data structure of a given 16 by 16 sparse matrices, and Actually, in our real experiment, we set a tile size of 16 by 16. So for both space cost and performance consideration. And on top of the tile data structure, we propose our algorithm called TileSpGEMM. Our TileSpGEMM can be divided into 3 steps, and the figure shows these 3 steps. Step 1 is to find the possibly non-empty tiles in C. And after this step, the tile pointer C and tile column index C in the higher level can be obtained. And step 2 is to determine the number of non-zeros and the row pointer array of each tile of C. And after that, the tile and C and mask C can be computed. And step 3 is to calculate the row and column indices and values of non-zero in C, and then the whole process is completed. So in step 1, we create a sparse matrix A prime according to original sparse matrix A, and we can find that the standard CSR format of A prime is totally equal to the higher level tile data structure of A. So in this step, we directly run an SPGEMM to multiply the high level tile structure of the 2 input matrices A and B. And the number of the non-zero in the resulting matrix C prime is actually the number of non-empty tiles in C. In this step, we considering the scale of the high-level multiplication, we directly call the Sparse library for its simpler interface and the better performance on small cases. And in step 2, when calculating a tile in C, we should find the corresponding tile row in A and tile column in B. And 2 questions here should be answered. The first one is how to find the tile pairs in A and B, and that should be multiplied. And the next one is how to generate the row pointer array and the number of non-zeros of each tile of C. So for the question 1, we in this paper choose to search the element of short array in the long array with binary search operation, and then record in the index of intersection of elements in their own position array. And for question 2, we use bit mask rather than the real B of each tile to reduce memory transfer cost of repeatedly loading structure information of tile in B. And then the atomic OR operation are performed on all the extracted line masks on the scratchpad memory to generate the mask of C. And after step 2, we can calculate the row and column index and values of non-zeros of C. And in this step, we design an adaptive method for selecting sparse or dense accumulators in on-chip memory. So we set a threshold, which is 75% of the tile size. And if the number is more than 8, like the tile C12, we firstly work on a dense form matrix and then save the result into its sparse form. And in this step, we don't allocate very large temporary space. And if the tile is relatively small, such as the tile 3-2, a sparse accumulator working on sparse tile is selected. And in this step, we don't allocate every very large temporary space either. And we test our TileSpGEMM and other 5 latest SPGEMM methods on NVIDIA RTX 3060 and 3090 GPUs. And the benchmark is 142 sparse matrices, requiring no less than 1 billion floating point operations when performing AA and AA transports. And besides, we select 12 classic matrices. And as we can see, the TileSpGEMM and SPEC can complete all matrices, and our method performs much better than the other 5 methods. And the scalability of our method is also much better than PH-Sparse, but a little worse than NSparse and SPEC. And to conduct a detailed analysis, we plot the performance comparison 18 representative matrices. And as we can see, TileSpGEMM can complete the 5 large-scale matrices and outperform much better. And this is because our method naturally avoids the allocation of temporary products. And as for the classic matrix web-based, our method also runs twice faster than the spec, which is a great improvement in recent years. The peak runtime cost on 18 matrices is shown in the figure. And as we can see, TileSpGEMM often use less space and finishes earlier. And the comparison of space cost and format conversion time, it also shows that our tiled data structure is a very efficient way. We also compare TileSpGEMM with Sparse, which is a relatively new SPGEMM work designed for using half precision and dense tensor cores on modern GPUs. And we tested 16 matrices listed on the Sparse, and the experimental results show that our method runs faster than Sparse on all 16 matrices. And make a conclusion in the final. Our TileSpGEMM stores the sparse matrix as a tiled format and avoids the 3 performance issues. The experimental data showed that our TileSpGEMM outperforms other 5 latest SPGEMM methods. And that's all. Thank you very much for your time.